Let's talk about radio. So up here, we have a picture of a woman. Now, it's important to realize that when radioactivity was first discovered and then used, and they found that it could help fight cancer, people thought, oh my goodness, we found this wonderful health benefit that we didn't even know. Radioactivity is good for you. They had creams and beauty products all touting with radiation. So with natural radioactive elements in it because you don't want to get cancer, so we put it in here to prevent cancer. People thought it was great. But there were some issues that they noticed, especially with the Radium Girls. There was a movie made a few years ago called Radium Girls, and these young women were hired to paint dials on watches that glowed in the dark and they were paid based on the number of watches that they completed. Now, these girls were painting the dials with radium because being radioactive, it naturally glowed in the dark. Your glow in the dark things are not made with radioactive materials anymore. So they said you need to paint the dials on the faces of the watch, and to get a finer point, put the paintbrush in your mouth to get that point on your paintbrush. So they are painting their watch faces, and they start getting really sick, really, really sick. And they're noticing that they're getting cancers, they've got their teeth falling out, they're bleeding, and it was just horrible, horrible things happening to them. And they tried to cover it up. They tried to say, no, no, it's fine. And it took hundreds of women standing up and saying, this is wrong. You're making us sick. We need to stop before it actually happened. So radium decays into radon, which is emitted as a gas. Now, you have contractors who build houses, and they should be certified by the National Radon Safety Association board, because if they are, then they'll know how to mitigate risks. Now, radon gas is in the ground naturally, but sometimes it can get into your homes. So if you have a basement especially, it's a good idea to have a radon detector just so that you could be aware of of what is coming into your house. It's the second leading cause of lung cancer in the United States. You cannot see it, you cannot smell it or taste it, but just because you can't see, smell, or taste it doesn't mean it can't be dangerous. Natural gas, we can't see or smell or taste it, but the company adds an odor to the gas so that we know if there's a leak. So that's why you say, I smell gas. It's because the company adds the odor because they don't want a dangerous situation. Since radon occurs naturally in the ground and we don't use it for other things, that is why we don't smell or taste it or see it. So one out of every 15 homes have high radon levels, and it's a good idea to get that radon detector. Just like you have smoke detectors, have a radon detector in your home for safety. Now, radioactivity cannot be seen, heard, or touched, and it has no taste or smell, just like with radon. The half-life is the time it takes for half of a given amount of a radioactive isotope to undergo decay. Half-lives can be fractions of a second to billions of years. Here is the formula for calculating half-life. So y equals 1/2 to the n, or T1/2 equals T over n. Y is a fraction of radioactive material left. N is the number of half-lives, and the T1/2 is the half-life time. So as we look at this, if we graph the half-life, you can see that if we started with 10 grams and say the half-life is 5 years, after 5 years, we have 5 grams left. After another 5 years, we have 2.5 grams left. After another 5 years, so 15 years total, we have 1.25 grams left. After another 5 years, so up to 20 years, we have 0.63 left. And so on until it's completely decayed. Half-lives can be billions of years, remember. So if it has billions of years, it's going to be around for a long, long time. Now, carbon-14 dating is used to determine the ages of fossils because all organisms take in carbon during their lifetime. Most carbon taken in by organisms is a stable form, which is carbon-12 or carbon-13, but 1 in a million is actually carbon-14. And that rate remains constant. If you sample all the carbons in a million carbons, you're going to find carbon-14. In carbon-14 dating, the fraction of carbon-14 that remains in material is measured and then compared with how much was in the material when it was alive. So they just do a comparison. They're like, oh, here we have a 1 in 20 million sample instead of 1 in 1 million sample. How old is this material then? The half-life of carbon-14 is 5,730 years. But if we wanted to date objects more than 60,000 years, we can't use carbon-14. We'd have to use some other isotopes because carbon-14 would be completely gone by the time 60,000 years passed in that specific fossil. So here are some other isotopes and their half-lives. You can see that tritium, which is a radioactive hydrogen, has a half-life of 12.25 years. It emits through beta radiation. Carbon-14 is beta radiation, and it's 5,730 years. Phosphorus-28, you can see how tiny that is, 0.28 seconds. And it does positron emissions. Positron is basically a positive electron. Phosphorus-32 is 14.3 days. Beta particles. For very old fossils, they'll use potassium-40. So you can see 1.28 times 10 to the 9th years, that's a long time for a half-life. So it's still going to be around no matter what. And then you have a bunch of others. All right, so let's do some practice questions here. A sample, I want you to try to answer these and then come back and check them. A sample of radioactive isotope has a half-life of 10 years. How much of the original sample remains after 30 years? Now, if you remember on a previous slide, and you should have these in your guided notes, we have the formula y equals 1 over 2n. So this will tell you the fraction of the radioactive material that's left. So we have y equals 1 over 2n. We know that we want to know how much is left. So it's going to be 1 over 2. How many half-lives have passed? 10, 20, and then 30. So 1, 2, 3 half-lives have passed. So it's going to be 1 over 2 to the third. So this will be 1/8 of the sample will remain at that point. Because every 10 years is a half-life. You could also say 30 divided by 10. That gives you 3 half-lives. But 1/8 of the sample is left. So here, the next question says if you start with 100 grams of a substance and it has a half-life of 5 days. How much remains after 10 days? Well, you know that 2 half-lives have occurred because 10 divided by 5 equals 2. So 2 half-lives have occurred. So after 2 half-lives, how much do you have left? So that's where you can say y equals 1 over 2 squared. And that's 1/4 of it left. What's 1/4 of 100 grams? So 100 grams times 1/4 would give us 25 grams, which is B. All right, let's look at the next one. A radioactive element has a half-life of 2 hours. So the half-life equals 2 hours. How long will it take for 75% of the sample to decay? So we only want 75% of it, or we want to know what it will be for 75% of it. So say we start with 100 grams. So there are a couple ways we could do this. Oh, here. Say we start with 100 grams. After 1 half-life, we have 50. After a second half-life, we have 25. So if it's 2 hours, this was 2 hours, this was 2 hours. After 4 hours, 75% of the sample has decayed. If you have questions, let me know and we can review that. Let's go on and we're going to talk about the power of the nucleus with fusion and fission. Now, nuclear reactions involve enormous energy changes. So E equals mc squared was Einstein's theory of relativity, and energy equals mass times the speed of light. We know that the speed of light is equal to 3 times 10 to the 8th meters per second. That's a lot. Nuclear fission is the splitting of an atomic nucleus into two or more larger fragments. So we have a neutron taking aim at uranium-235. It splits. This is a very, 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 very fast neutron. Think of it like you have a rubber band and you've stretched it out almost to its limit. Not quite. And someone cuts it with a pair of scissors. What's going to happen? It's going to just release all of that potential energy. That's what happens. The scissors is like the neutron here. It's coming, it's going to just release so much energy with so much power. And here you can see all that power, all that energy that's released, along with 3 more neutrons and a barium isotope and a krypton isotope. Now, these 3 other neutrons have a ton of energy, and it's like a domino effect. So if there are any other uranium atoms around, it's going to split them and continue releasing those 3 extra neutrons and continue. It's a chain reaction, and it will not stop until all of them have been split. This is what nuclear reactors use. They use uranium-236, and they use the neutron to come in and split the nucleus. And they use control rods to control how much uranium they're splitting at a time. Now, atoms of 2 different elements are created along with more neutrons. Like I said, it's a chain reaction. It's going to keep going until it can't react anymore. Now, as World War II started, the race was on to find a way to sustain fission in a chain reaction. This chain reaction is a continuing series of reactions in which each produces a product that will react again. Each neutron produced in the first reaction has the potential to cause a fission of another nucleus, and for a chain reaction to take place, there has to be enough fissionable material present for some of the neutrons produced to be able to collide with other nuclei. You might have some some extra atoms there, but if it's not in the area, you're going to, if it's not in the path of the neutron, the fission will stop. Now, if the chain reaction takes place too quickly, an explosion will result and release an enormous amount of energy. Like atomic bombs work this way because it's not controlled. It's just here, just do it. That's whenever you get the explosion. So if someone is not being careful in a nuclear reactor, that's whenever you have a meltdown. But we have all these safety protocols in place to prevent that from happening. If the rate of the fission chain can be controlled to release energy slowly, that energy then can be used to heat material, such as water, in use of power plants, which is what we do. Nuclear reactors then are used to extract energy from a radioactive fuel to create electrical energy. It is highly efficient, and about 20% of energy in the US comes from nuclear reactors. There are some countries that have 90% of its energy coming from nuclear reactors. I think Belgium is one of those. They didn't want to rely on foreign power, so they decided to build nuclear reactors to power their country. Uranium and plutonium are used for nuclear fission reactors. Nuclear fusion is the opposite of fission. You have two or more nuclei combine to form a larger nucleus, and it's a process that produces energy in stars. So here is what we have. We have our deuterium plus, here's our deuterium, plus our tritium, and it produces helium plus an extra neutron plus energy. That's how our stars burn. They'll burn up all of their hydrogen and turn it into helium, and then they'll start burning helium and creating other elements. That happens as they age, as they burned up all their fuel. Now, deuterium is an isotope of hydrogen that has a mass of 2, and tritium is an isotope of hydrogen with a mass number of 3, both of which are radioactive. Now, no radioactive products are created in nuclear fusion, so waste disposal is a lot simpler than nuclear fission. Fusion is also easier to control than fission. But here's the drawback. Fusion is much more difficult to start. You need temperatures of 200 million kelvins, which of course would melt our reactors. For years, decades, scientists have tried to find a way to do cold fusion. So do fusion in a cooler reactor. But they have not been successful. If you could somehow create cold fusion, you would be a very wealthy person because you would have unlimited power. Now, if there was an old TV show in the 60s called The Saint, and then in the 90s, they made a movie, The Saint, with Val Kilmer. And the premise of that was trying to find the formula for cold fusion. Now, use of radioisotopes. We use them in medicine. So if you ever had a PET scan or had a tracer in you, you had radioisotopes. Like I had a test to see how the function of my gallbladder was before I had to take it out. So I had a tracer in me, and they watched the tracer to determine the function of my gallbladder to see if I needed it removed or not. We use tracers to follow chemical reactions in the body to identify abnormalities. If you have swallowing issues, sometimes they could give you a barium swallow test, which that's a tracer so that they can see the process of you swallowing and help determine the issue. The majority of nuclear waste actually comes from hospitals. It's not from nuclear power plants. It's actually from hospitals because of all of the nuclear tests that they do there. Between the PET scans and your tracers. And many people are surprised by that. They think of the radioactivity of radioactive waste from nuclear power plants. That's not the case. Hospitals are the ones who produce the most nuclear waste. Now, we're more likely to be saved by some form of nuclear medicine than we are to be killed by the effects of radiation because we use radiation as a form of cancer treatment. So many people have their lives saved. You have more people who have been saved by the effects of radiation rather than killed from radiation. We also use tracers to test structural weaknesses in mechanical equipment and to follow pathways of pollutants on Earth. So there are lots of beneficial uses of radioisotopes. We also do food irradiation. We can irradiate food with gamma rays because gamma rays kills organisms. And so we can sterilize food and surgical instruments. Now, it's important to note that these surgical instruments and food do not become radioactive. It just kills the bacteria. Exposure of radioactive elements can be hazardous to your health. So like the technicians for the X-ray technicians, for example, they use badges that have a counter that counts how much radiation they're exposed to. And after a certain limit, they're no longer allowed to be in be administering those x-rays because we want to keep them safe as well. The more energy radiation has, we know, the more dangerous it tends to be. So let's talk about these sources of radiation. There's actually constant radiation that's bombarding us, and we don't even realize it. Some are made by bombarding other elements with small particles that have been accelerated to high speeds. Others are byproducts from nuclear reactors. And then, as I said before, we constantly have low levels of background radiation because some of the cosmic rays from space make their way down to Earth. And those cosmic rays are background radiation. And many other things have tiny amounts of radiation in them, like bricks, wood, fabrics, food, because again, you have radioisotopes that have been taken into different organisms and different minerals because everything gets recycled in the earth. And so you naturally have some radioactive isotopes, not a ton, but you do naturally get some radioactive isotopes in plants, in fabrics as a result of them being in plants, because of course, fabrics are made from plants. All right, so let's answer some questions. I want you to try answering these on your own and then come back and check. What is nuclear fission? Okay. Fission is the splitting of a heavy nucleus into smaller nuclei. Fusion is the opposite. That's where you're combining things. Number 2, which of the following is true about nuclear fusion? Well, we use fission in nuclear power plants, so that's not true. Fusion doesn't split a nucleus. It does not produce radioactive waste, but it does require high temperatures and pressure, which is why it's so difficult to achieve here on Earth. Which of the following equations represents a fusion reaction? So remember, fusion is a combination of two or more things. This first one is the fission of uranium, because with fission, you shoot a neutron at uranium. D shows a decay. C shows a decay, radioactive decay. This right here in B, that's the only fusion reaction that's shown. All right, I want you to try to answer these and then come back and see if you're correct. Which of the following correctly represents a nuclear fission reaction? Same thing. All right, we know that it's two or more elements combining to one. C is the only one that does that. 5, what is the missing product in this fusion reaction? So we're going back to the first lesson. This is just a nice little review. Remember, we have 2,1H plus 3,1H Deuterium plus tritium produces something in a neutron. Well, this total right here is 5. This has 1. So 5 minus 1 gives us a mass of 4. 1 and 1 is 2. This total is 2. 2 minus 0 equals 2. So what element has an atomic number of 2? If you look on the periodic table, that would be helium. So the answer would be A. If you have questions, please let me know. I'm happy to help. Enjoy the rest of your week.